You know, when most people see a subarray problem, they jump straight to the hard way. They write these nested loops. They calculate the same sums over and over and over again, and they run out of time. But what if I told you there's a secret? A single, beautiful mathematical idea that unlocks this entire class of problems, turning them into these elegant, single-pass solutions. Today, we're going to uncover that secret.
And it all really comes down to this one question. How can we use what we've already seen, our history, to instantly know something important about where we are right now? Just keep that question in the back of your mind as we go through this. Okay, so let's dive right in by setting up our core problem. Now, it looks pretty simple on the surface, but trust me, it's the perfect way to really get this powerful pattern.
That's it. That's the whole question. We're not trying to find how many of them there are or which one's the longest. It's just a simple yes or no. Does a zero-sum subarray exist anywhere in there?
So what's the first thing that pops into your head? For most of us, it's, well, just check everything. Check every single possible subarray. But as we're about to see, that obvious path is a trap. The logic is super straightforward, right? You pick a start, then you pick an end. You add up all the numbers between them and you check, hey, is that 0? And then you just do it again and again and again for every single combination you can think of.
And yeah, this will eventually get you the right answer, but it's so incredibly inefficient. It's got no memory. It has no idea what sums it's already calculated. It's just grinding away, redoing the same work constantly. And because of that, it is painfully slow.
Okay, now for the big turning point. Let's just throw that whole inefficient mess out the window and introduce the one single idea that changes absolutely everything.
This right here is our secret weapon, the prefix sum. And it's exactly what it sounds like. It's just a running total. As we walk through the array, we just keep a little tally of the total sum from the very beginning all the way up to our current spot.
So, here's where the magic happens. Think about it. If the sum from the start all the way to say point L is 10, and then later the sum from the very same start all the way to point R is also 10, what does that tell you about all the numbers that were between L and R? It means they must have all added up to exactly 0. They canceled each other out.
And this leads us to this powerful absolute truth about this entire problem. A subarray that sums to 0 exists
If and only if one of our prefix sum values shows up more than once. That's it. It's a brilliant insight. A repeated prefix sum means pure cancellation happened. The net effect of everything in between was a big fat 0.
I really want to hammer this point home. This is not some clever little coding hack or a neat party trick. This is a fundamental mathematical property. The problem of finding a zero-sum subarray is the exact same problem as finding a repeated prefix sum. They are one and the same. So we've got the math, we've got the theory. How do we actually turn this beautiful truth into a blazingly fast, single-pass algorithm? Well, let's build it.
Okay, our strategy is beautifully simple. We're just going to walk through the array one time. As we go, we'll keep our running prefix sum, and we use a hash set, think of it as our memory, to remember every single prefix sum we've seen before. And that little step, initializing the set with a 0, that's critical. It's like our virtual starting point, and it lets us catch any zero-sum subarrays that start right at the very beginning of the array.
All right, let's trace this out. We start with our prefix sum at 0, and our set of seen sums has just that 0 in it. First number is 4. Our new prefix sum is 4. We haven't seen it, so we add it to our set. Next up is 2. The prefix becomes 6. Also new, so we add that to our set too. Okay, next we process -3. Our running total, that prefix sum, drops from 6 down to 3. Is 3 in our set? Nope. It's a new value, so we just add it to our history and keep on moving. All right, here it is. This is the key moment. We add 1 to our current prefix of 3, and the new prefix sum is 4. Now we ask the most important question of the whole algorithm. Have we ever seen the number 4 before?
Yes, we have. It's a collision. Our set immediately tells us, hey, I've seen a prefix sum of 4 before. And that means the numbers that came between that first time we saw 4 and this time, the subarray 2, -3, 1, they absolutely must sum to 0. And just like that, in a single pass, we're done. We found our answer.
But look, this is so much bigger than just this one little problem. What we've really uncovered here isn't just a trick. It's a versatile, powerful pattern that can be tweaked to solve a whole family of problems.
The key realization here, the big idea, is that we weren't just storing plain old numbers in our set. We were storing a compressed version of our journey through the array. We were hashing our history. And by remembering the past state, we could make an instant decision about the present.
And check out just how flexible this pattern is. If you want to count all the zero-sum subarrays, you just switch from a set to a hash map and store the frequency, how many times you've seen each prefix sum. If you want to find the longest one, you use a map to store only the first time you saw each prefix sum. It's the same core logic, you just change what little piece of history you decide to remember.
And that brings us to the final, most powerful insight of all. This whole zero-sum problem, it's just a special case. The real pattern is about finding a subarray that sums to any target value k. The only thing that changes is the question you ask. It's the same engine, you're just putting different fuel in it.
So I'll just leave you with this thought. This prefix sum pattern, it's a fundamental tool for your toolkit. Once you really, truly get it, you stop seeing dozens of different, disconnected problems. You start seeing the same underlying structure, just wearing different disguises. So what other problems could you solve if you stopped trying to memorize solutions and started looking for the patterns?